Welcome! In this video, we'll dive into problem number 598, titled Range Addition 2. This problem challenges us to optimize operations on a matrix, testing our understanding of array manipulation and algorithm efficiency. Stay tuned as we explore different approaches to solve it. In this problem, we start with an MXN matrix where all elements are initialized to 0. We are given a series of update operations, each represented by a tuple, A, B. Each operation increases the value of every element in the submatrix that starts from the top left corner, 0, 0, and ends at the bottom right corner, A1, B1. Our goal is to determine how many cells in the resulting matrix contain the maximum value after all these operations are applied. The input includes the dimensions of the matrix M and N, as well as a list of operations ops. The output is a single integer, which is the count of the maximum elements in the matrix. Let's look at an example to make this clearer. Suppose the matrix has dimensions m equals 3 and n equals 3, and the operations are 2, 2, 3, 3. For the first operation, 2, 2, we increase the values in the submatrix that spans from 0, 0 to 1, 1. This results in the following matrix, 1, 1, 0, 1, 1, 0, 0, 0, 0. The cells within this submatrix are incremented by 1, while the rest of the matrix remains unchanged. Next, we apply the second operation, 3, 3, which increments all elements in the submatrix spanning from 0, 0 to 2, 2. This modifies the entire top left 3 by 3 section of the matrix, resulting in the following, 2, 2, 1, 2, 2, 1, 1, 1, 1. The maximum value in the matrix is now 2, and it occurs within the 2x2 submatrix from 0, 0 to 1, 1. This submatrix contains 4 cells with the maximum value, so the output for this example is 4. Here's another example. This time, the matrix dimensions are m equals 4 and n equals 5, and the operations are 3, 4, 2, 3. For the first operation, 3, 4, the values in the submatrix from 0, 0 to 2, 3 are increment. The resulting matrix looks like this, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. Then, the second operation, 2, 3, increments the values in the submatrix from 0, 0 to 1, 2. The updated matrix becomes 2, 2, 2, 1, 0, 2, 2, 2, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. The maximum value is 2, and it is found in the 2x3 submatrix from 0, 0 to 1, 2. This submatrix contains 6 cells, so the output is 6. Now consider a scenario with no operations. If m equals 5 and n equals 5, and the ops list is empty, the matrix remains unchanged with all elements equal to 0. The maximum value in this case is 0, and since every cell in the matrix contains this value, the count of maximum integers is simply the total number of cells, which is 5x5 equals 25. Thus, the output is 25. Finally, let's discuss some edge cases. If there are no operations, the maximum value will occur in all m*n cells, as the matrix remains unmodified. For a single operation, the maximum value will be concentrated within the submatrix defined by that operation. When m or n are large, the algorithm must efficiently handle these dimensions without directly simulating the updates for every cell. For overlapping operations, the maximum value is determined by the smallest dimensions a and b among all operations, because the overlap of all submatrices defines the region with the highest value. To begin, let's consider the brute force approach. The intuition here is straightforward. We directly simulate the effect of each operation on an MXN matrix. To explain this, imagine starting with a matrix filled with zeros. For every operation, A, B, we update the submatrix from 0, 0 to 1, B1, by incrementing all its elements. After processing all the operations, we determine the maximum value in the matrix, and then count how many times this maximum appears. While this method is conceptually simple, the computational cost is significant. Specifically, the time complexity is proportional to the product of the number of operations and the size of the submatrices being updated. In the worst case, this can become O, K** m**n. Additionally, the space complexity is O, m**n, because we need to maintain the entire matrix. This makes the brute force approach impractical for large matrices or numerous operations. Now, let's discuss the drawbacks of the brute force approach and introduce the optimized solution. The main issue with the naive method is its inefficiency. Repeatedly updating large portions of the matrix becomes computationally expensive, especially with large inputs. To address this, the optimized approach avoids directly simulating the operations. Instead, we focus on the key observation that the maximum value in the matrix occurs in the region where all operations overlap. The dimensions of this overlap are determined by the smallest values of A and B across all operations. This allows us to bypass unnecessary computations. By iterating through the operations, we track the minimum A and B, which define the dimensions of the overlap. The count of the maximum value is simply the area of this overlap, calculated as min_A*min_B. This approach is not only more efficient but also leverages the problem's inherent structure to simplify the solution. The complexity of the optimized approach further highlights its advantages. The time complexity is OK, as we only iterate through the list of operations. The space complexity is reduced to O1, since we don't construct or store the entire matrix, we only maintain two variables, min_A and min_B. These improvements make the method highly efficient for large inputs. By focusing solely on the overlap dimensions, we avoid redundant computations and achieve a direct solution. This is why the optimized approach is the preferred strategy. While the brute force method is easier to understand, its inefficiency makes it unsuitable for scenarios with high constraints. The optimized solution strikes the right balance between simplicity and performance, making it an excellent choice for competitive programming and real-world applications where speed and resource efficiency are critical. To begin, let's set up the problem. We have a matrix of size mxn, initialized with zeros. The task involves applying a series of operations. Each operation is defined by two values, A and B, and it increments all elements within the submatrix from the top left corner, 0, 0, to the bottom right corner, A1, B1, by 1. After applying all the operations, the goal is to determine how many elements in the matrix contain the maximum value. One straightforward way to approach this is through a brute force method. We start by initializing the matrix, then simulate each operation by looping through the rows and columns of the specified submatrix, incrementing the values in those cells. Once all operations are complete, we iterate over the entire matrix to find the maximum value and count how many elements hold that value. Finally, we return this count as our result. While this approach is intuitive, it requires iterating over large portions of the matrix multiple times, which can become computationally expensive as the size of the matrix or the number of operations increases. The brute force approach, while functional, is inefficient because it involves nested loops over both the operations and the dimensions of the affected submatrices. This results in a time complexity of O(k*A*b), where k is the number of operations, and A and B represent the dimensions of the submatrix for each operation. For large matrices or a high number of operations, this can lead to significant computational overhead. To optimize, we can leverage a key observation: the maximum value in the matrix is determined by the overlapping region of all the operations. Specifically, the number of elements with the maximum value corresponds to the area of overlap in the smallest submatrix defined by all operations. Instead of updating the entire matrix, we can simply track the smallest A and B values across all operations. This insight allows us to drastically reduce the computational effort while achieving the same result. To implement this optimized approach, we start by initializing two variables, min_A set to the height of the matrix M, and min_B set to the width of the matrix N. These variables will be used to track the smallest dimensions of the overlapping submatrix. For each operation, A, B, we update min_A to be the smaller of its current value in A, and similarly, min_B to be the smaller of its current value in B. After processing all operations, the number of elements with the maximum value is simply the area of the smallest overlapping submatrix, which is given by min_A*min_B. This value is then returned as the result. Notably, this approach does not require any additional data structures, as we only track the minimum dimensions of the submatrices. By avoiding the need to simulate the matrix updates directly, we significantly reduce both time and space complexity. This works because the smallest overlapping region inherently determines the area with the maximum increment value. Analyzing the complexity, the brute force approach has a time complexity of O, k *a b, because it updates all elements within the submatrix for each operation. It also has a space complexity of O, m *n to store the matrix. In contrast, the optimized approach reduces the time complexity to O, k, as it only involves iterating through the operations once, and the space complexity is reduced to O, 1, since no matrix is required. Several edge cases should also be considered. If there are no operations, the matrix remains 0, and the count of maximum elements is simply m *n. For a single operation, A, B, the result is the area of the specified submatrix, A *b. If all operations cover the entire matrix, meaning A, B, for each operation is greater than or equal to m, n, the result is the total number of elements in the matrix, m *n. Finally, even if operations do not overlap, the algorithm correctly identifies the smallest overlapping region as the area of maximum value, ensuring accurate results in all scenarios. This solution for LeetCode problem number 598, Range Addition 2, efficiently computes the number of maximum elements in a matrix after applying a series of operations. The problem starts with an mxn matrix initialized to zeros. Each operation defines a submatrix, where all elements are increment. After applying all operations, the task is to find the count of elements with the maximum value. The code begins by checking if the ops list is empty. If no operations are provided, the entire matrix retains its initial state, and every cell has the maximum value of 0. Thus, the result is simply the total number of cells, m *n. Next, the algorithm determines the smallest dimensions, rows and columns, affected by all operations. This is because the submatrix that is increment by every operation is determined by the intersection of all A, B ranges in ops. For each operation, A, B, it updates min_row and min_call to track the smallest overlap dimensions. Initially, these are set to the matrix dimensions m and n. The final result is the area of this overlapping submatrix, calculated as min_row * min_call. This represents the number of elements in the matrix that received the maximum number of increments. This approach avoids modifying the matrix directly, making the solution highly efficient. The time complexity is O, k, where k is the number of operations, as we only iterate through the ops list. The space complexity is O, 1, since no additional data structures are used. This is the Java implementation of LeetCode problem number 598, Range Addition 2. The logic mirrors the Python implementation, focusing on finding the smallest submatrix affected by all operations. Key differences include the use of Java's primitive types, arrays for operations, and math.min for comparisons. The solution is efficient and concise, iterating over the operations to determine the minimum bounds and calculating the area of the resulting overlap. Here, we start by looking at a simple example where no operations are applied. The matrix is initialized as a 3x3 grid filled with zeros. Since the ops array is empty, no changes are made to the matrix. The condition if not ops checks for this scenario and directly calculates the total number of elements in the matrix by multiplying m and n. In this case, 3*3 equals 9. This means all elements in the matrix remain at their maximum value, which is 0, and the final result is simply the total count of elements, 9. Now, we explore an example with a single operation. The matrix starts as a 4x5 grid filled with zeros. We initialize min_row to 4 and min_call to 5, which are the dimensions of the matrix. The operation 3, 3 specifies that we need to add 1 to the top left 3x3 submatrix. To determine the boundaries of this submatrix, we update min_row to the minimum of the current min_row and the operation's first value, resulting in min 4, 3 equals 3. Similarly, min_call is updated to min 5, 3 equals 3. After processing this operation, the effective submatrix affected is a 3x3 grid in the top left corner. The area of this overlap submatrix is min_row * min_call is equal to 3 times 3 equals 9. Thus, the result is 9, as all elements in the 3x3 submatrix have reached their maximum value of 1. Next, we consider an example with multiple overlapping operations. The matrix starts as a 6 by 7 grid filled with zeros. We initialize min_row to 6 and min_col to 7, the dimensions of the matrix. For the first operation, 4, 5, we update min_row to min, 6, 4, equals 4 and min_col to min, 7, 5, equals 5, reducing the effective submatrix to a 4 by 5 top left grid. The second operation, 3, 4, further narrows the overlap, min_row becomes min, 4, 3, equals 3, and min_col becomes min, 5, 4, equals 4. Finally, the third operation, 2, 6, reduces the overlap even more, with min_row updated to min, 3, 2, equals 2 and min_col staying at min, 4, 6, equals 4. After processing all operations, the effective submatrix is a 2 by 4 grid in the top left corner, and its area is 2 * 4 equals 8. This gives us the result of 8. To visualize the result of the previous example, the operations have reduced the effective matrix to a 2 by 4 submatrix in the top left corner. This means only the first 2 rows and the first 4 columns of the matrix are affected, and all elements within this submatrix have the maximum value of 1. The rest of the matrix remains untouched, filled with zeros. The resulting matrix structure reflects this overlap, with the top left 2 by 4 submatrix highlighted. The final output of 8 represents the total area of the region where all elements have been maximized. This concludes the solution, demonstrating how the operations iteratively shrink the effective region to calculate the result. To analyze the time complexity of our solution, we start with the initialization of 2 variables, min_row and min_col. These are straightforward assignments, each taking constant time, or O1. Next, we iterate through the list of operations, ops. For each operation, we calculate the new minimum row and column indices using the min function, which has a constant time complexity per call. Since there are 2 min operations for every entry in ops, the total time spent in this loop is proportional to the number of operations, denoted as k. Finally, the result is calculated as the product of min_row and min_col, which is again a constant time operation. Altogether, the best case time complexity is O1, which occurs when the list of operations is empty. In the worst case, where ops contains k operations, the time complexity becomes OK. Thus, the overall time complexity of the solution is OK, where k represents the number of operations in the input list ops. Now, turning to space complexity, we begin with the input storage. The dimensions of the matrix M and N, as well as the list ops, are part of the input and do not contribute to additional memory usage. The solution uses 2 auxiliary variables, min_row and min_col, to track the minimum dimensions affected by the operations. These are simple scalar variables and require constant space, or O1. Importantly, the algorithm does not allocate any additional data structures such as arrays or matrices. Therefore, the total auxiliary space complexity is O1, as the memory usage remains constant regardless of the input size. When comparing this optimized approach to a naive, brute force solution, the differences become clear. In a brute force approach, we would simulate the operations directly on an MX and matrix. For each operation, A, B, we would increment all elements in the submatrix defined by 0, 0, 2, 1, B1. This would require iterating over potentially large portions of the matrix for every operation, leading to a time complexity of O, K *M*N. Additionally, storing the matrix would require O, M*N space, which can be prohibitive for large inputs. In contrast, the optimized approach avoids directly simulating operations. Instead, it calculates the overlap of all operations as min_row and min_col, significantly improving efficiency. The time complexity is reduced to OK, as it only requires a single pass-through ops, and the space complexity is reduced to O1, as no matrix or other data structures are used. The mathematical reasoning behind this optimization lies in the observation that the maximum value in the matrix after all operations is determined by the smallest submatrix affected by all the operations. This submatrix is defined by the minimum row and column indices across all operations. By iterating through ops just once to calculate min_row and min_col, we effectively determine the size of this submatrix without having to simulate the operations themselves. This insight allows us to achieve a time complexity of O, k, and a space complexity of O, 1, making the solution both efficient and scalable for larger inputs. When working with this problem, there are a few common mistakes to watch out for. First, using a brute force approach to simulate updates directly on an MXN matrix for every operation may seem straightforward, but it becomes inefficient as the matrix size and the number of operations grow. This leads to a time complexity of O, k*m*n, which can quickly become unmanageable. A better approach is to use prefix sums or difference arrays to optimize updates and minimize redundant computations. Another mistake involves misunderstanding the problem's constraints. If the operation bounds, a, b, exceed the matrix dimensions, it can cause out-of-bounds errors. To avoid this, always validate the input constraints and ensure operations are within the allowable range. Lastly, incorrect matrix initialization is a common pitfall. Starting with a non-zero matrix, perhaps by reusing a matrix from a previous test case, can produce invalid results. To prevent this, always initialize the matrix to 0 or follow the problem's specific requirements before performing any operations. Indexing errors are another frequent issue to be mindful of. Off-by-one errors, especially when dealing with submatrix operations, can lead to partial or incorrect updates. These often arise when boundary conditions aren't properly included or when ranges aren't clearly defined as inclusive or exclusive. To address this, carefully verify your indexing logic and ensure it aligns with the problem's requirements. Additionally, it's important to handle edge cases correctly. Scenarios like m equals 1, n equals 1, or having no operations at all can often be overlooked, leading to runtime errors or inaccurate results. To mitigate this, explicitly test edge cases and include condition checks. For instance, you might include a check like if operations equals to handle cases where no updates are provided. Paying attention to these details can help you avoid common pitfalls and build a more robust solution. Now, let's consider some insights that can help you excel in interviews with this problem. One key point is demonstrating an understanding of trade-offs. While a brute force solution is simple and easy to explain, it's not efficient for large-scale problems. Being able to discuss how optimized techniques like prefix sums or difference arrays reduce time complexity shows your depth of knowledge. It's also helpful to highlight how reducing redundant operations, such as updating only the boundaries instead of the entire submatrix, makes your solution scalable. Additionally, clearly explaining how you handle edge cases, like empty operations or single row or single column matrices, showcases your attention to detail. Lastly, be prepared to articulate the time and space complexity of your solution. For example, explaining how an optimized approach achieves O, m*n plus k, time complexity and why it's an improvement over brute force demonstrates a strong grasp of algorithmic efficiency. This problem also shares similarities with several related problems, which can deepen your understanding and help you identify patterns. For instance, in problem 598, Range Addition 2, the focus shifts to finding the maximum element in the matrix after performing a series of operations, offering a variation on the same theme of matrix manipulation. Problem 370, Range Addition, is a one-dimensional version of this problem and emphasizes the use of a difference array to optimize range updates. Similarly, problem 304, Range Sum Query 2D, Immutable, involves querying the sum of submatrices efficiently by leveraging prefix sums. Lastly, problem 1109, Corporate Flight Bookings, applies a difference array technique to handle range updates in a one-dimensional array. Exploring these related problems can provide valuable insights and reinforce your ability to solve a variety of range update challenges. Finally, let's explore some alternative approaches and their trade-offs. One popular method is using a prefix sum or difference array. Instead of updating every cell in the submatrix directly, you increment only the boundaries and then compute the final values in a post-processing step. This approach significantly reduces the time complexity to O, m*n plus k, but it can be slightly more complex to implement. For one-dimensional variations, a segment tree can be an efficient tool for handling range updates and queries. While it offers dynamic updates, its implementation is more intricate compared to a difference array. Another advanced technique is the binary index tree, or BIT. For two-dimensional problems, a 2D bit can handle both updates and queries efficiently, typically in O, log, m, log, n, time. However, this method is the most complex to implement of the three. Choosing the right approach depends on the problem requirements, the trade-offs you're willing to make, and your familiarity with these techniques. Great job following along. We covered problem number 598, reviewed the brute force approach, and discussed its implications. Remember, practice is key, so keep solving similar problems to sharpen your skills. Don't forget to like, subscribe, and stay tuned for more great content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!